A robust predictions problem. We're looking at a very simple model of a first price auction, and we want to find minimum revenue of that auction. And the way we're doing it is by minimizing revenue over all Bayes correlated equilibria. The auction model is there are n bidders, and they're bidding for a single unit of a good, and they all have exactly the same value for the good, which is a V drawn from a distribution F that has a density. And the players are just going to submit bids. The winner is chosen randomly from the set of high bidders, and the winner has to pay the bid. And in the last lecture, we did a lot of work, and we looked at simulations that led us to conclude that the worst case for revenue, the model of information in the auction and the equilibrium that's going to lead to the smallest expected revenue for the seller, has a very simple form. So I guess I should add for people who weren't here last time, our exercise is we haven't specified what the information is of the bidders yet, and we're treating that as a free variable, and we're treating the equilibrium as a free variable as well, and we're looking across all models of information and all Bayes-Nash equilibria and trying to find the one that's going to induce lowest revenue for the seller. And we concluded last time that 0 was impossible. Revenue has to be bounded away from 0 for the seller in every equilibrium. So there's some non-trivial lower bound, and we want to find out what that is. And we concluded that it looks like the worst case model from the perspective of expected revenue has the form where the bidders get independent signals that are drawn from this particular distribution here, the nth root of the cumulative distribution of the value itself, and the signals are correlated with the values so that the value is equal to the maximum of the signals. So we've chosen this nth root distribution precisely so that the distribution of the highest of these independent draws has the same distribution as the distribution of the value. Okay. It's F, yeah. Okay, so, and then we defined G to be the distribution of the highest of n minus 1 of these draws. So from the perspective of any one of these bidders, this is the distribution of the highest of the other signals. And we concluded that there's an equilibrium in monotonic pure strategies where all of the bidders, each bidder bids as a function of their signal, the expectation of the highest of the other signals conditional on it being less than their own signal. And we noticed that there was actually a nice correspondence between this model and an independent private values model. This would be the equilibrium if the bidders interpreted the signals as their own values. So your behavior would be the same if you thought that your signal was your own value. In fact, it's not. The value is the maximum of all of the signals, but nonetheless, the bidders, in spite of the value being much higher in the independent private value model, you don't bid anymore. So in a sense that, one reason why this, or one intuitive way to think about why this is a bad equilibrium for the seller is that bids are low relative to expected values, meaning that there's a lot of shading effectively to avoid a winner's curse. Okay, so we argued that this is an equilibrium, and then the question is, why is this an equilibrium? So why is this the worst case for the seller? And that's the last piece that I owe you guys from last time. And the argument is that we can identify a lower bound on expected revenue, and then this equilibrium attains that lower bound, so therefore it has to be minimum revenue across all models of information equilibria. Now we want to get this lower bound by making the problem simpler. Remember, we were saying we could find the minimum just by taking a minimum across all Bayes correlated equilibria, but that's a very large and complicated object. It's an incomplete information correlated equilibrium. It's well behaved in an analytical sense because there's a convex set of these correlated equilibria. They're described by a family of linear inequalities, but it's a large family. It's a continuum of these linear inequalities. So the way we're going to make our lives easier is, first of all, instead of minimizing revenue over Bayes correlated equilibria, we're just going to look at a marginal of that correlated equilibrium, and it's the one that we care about the most, the distribution of the winning bid. Okay, the distribution of the winning bid is going to tell us what revenue is, and it turns out that's a rich enough description of the equilibrium to impose enough constraints to hold us to the true minimum. And then the other is, from those simulations that we did, we got a good sense of what are the critical incentive constraints that are pinning down minimum revenue. And we found that actually all of the bidders at this, in this revenue minimizing model of information equilibrium, they're indifferent between their equilibrium bids and any higher bid. Okay, and in fact, those were the only binding incentive constraints for the bidders. So we want to use that upward indifference in order to constrain the distribution of winning bids in such a way that we get to precisely the expected revenue in that construction. So let's define script H to be the set of winning bid distributions. So this is the distribution of the highest of the n bidders' bids that could be induced by some base correlated equilibrium. So as some examples, this H is going to contain all of the winning bid distributions in the constructions we did last time, and in particular, it's going to contain the induced distribution from this putative worst case, which is okay, so in that worst case, the highest of the signals is the value. So the winning bid is just going to be that equilibrium strategy, beta lower bar, evaluated at the value. So the winning bid is a deterministic function of the value. And then the distribution over the winning bid is simply the likelihood that the value is less than the critical value at which this would be the equilibrium bid. Yeah?
It turns out there is a difference.
Yeah.
Appeared a lot in the information design problem. So what is the intuition of making the leaders indifferent between any winning bid?
Well, they're not indifferent between any winning bid. They're indifferent between what they end up doing in equilibrium and any higher bid.
Okay, all right.
I mean, the specific intuition in this model is that, if the distribution of winning bids was too low, in a sense, was lower than what you could get in equilibrium, well, that would mean that, someone could increase their bid by a relatively small amount and increase the probability of winning by a large amount. And that would be appealing if, bids were sort of too concentrated at the low end. So that's a general intuition for why upward constraints are critical. Why are they the only ones that matter? Why is it possible to make bidders indifferent to any upward deviation? I mean, that's a little remarkable, and it just happens to be, a beautiful and simplifying feature of this problem. But in general, in information design, you end up with indifference just because those are the, those are the constraints.
The bid and any bid above.
Correct. Yeah. That's right.
But a general answer to a question, why do you get a lot of constraints binding, is just that if you're looking at extreme points, correlated
Yeah.
equilibrium,
Exactly.
Yes,
Those incentive constraints are what are defining the base correlated equilibrium. But,
these are the relevant constraints for that problem.
yeah, exactly which constraints, is hard to say a priori. But
That's because it's correlated? Is the correlated the key here that gives you the binding ones are the ones above?
sure, absolutely. So
That's not true for the Nash, for the standard incentive constraint, right?
it depends on what model of information we're talking about. So, this correlated equilibrium concept is encapsulating varying the information that the bidders have about the value and varying the type space as we vary the Bayes-Nash equilibrium as well. So, we've identified a particular type space and equilibrium where you get that large upward indifference.
Suppose it was a Nash equilibrium problem, but the seller wanted to minimize his revenue.
And gets to choose the information?
No,
Oh,
then you would get.
it depends on the
You
information.
might get.
You don't get to the extreme point of itself, so minimize, maximize, that's not the issue.
It depends on the information you have, whether, which constraints are going to matter in the Bayes-Nash equilibrium. If it was an,
Intuitively, I mean, that's the intuition I got from Steve at the break. So I'm just taking it
Ah.
from you on Friday.
I don't know, he's a shady guy. I wouldn't trust everything he tells you. No, I'm just kidding. I'm just kidding.
Right, you want to push the bids as low as possible.
Right. I guess I don't understand if we're not treating the information as an endogenous object. What is the tool that the seller has? Or this isn't a mechanism design problem, it's an information design problem. We fixed the mechanism and we're trying to strain that particular mechanism as much as possible to lower revenue. So the only feature of the model that's
Yes.
endogenous is information.
Okay.
Okay. So this is what we're gunning for. And then, okay, so there's an order on distributions over winning bids, the first order stochastic dominance order, which basically says that one distribution H is dominated by another if H has a lower CDF at every point. An equivalent way of saying that would be, this is a typo here, but the equivalent way of saying is that for any increasing function, the expectation under H is higher than under H prime. Okay. And the theorem that's going to imply that we've gotten to the lower bound is that for any winning bid distribution that could be induced by equilibrium, by a base correlated equilibrium, that H is going to first order stochastically dominate this H lower bar. Okay? Meaning that the expectation of the winning bid is going to be higher under any equilibrium winning bid distribution than under H lower bar. And that means that expected minimum revenue is just going to be the expectation of the winning bid under this H lower bar.
And H lower bar is the one you get from Fs to the power 1 over n?
Correct, from that particular construction. It was defined that way. Yeah. Okay, so we actually need a little bit more than just the marginal over the winning bid. We're also going to need to know how the winning bid is correlated with the value. So this H of B given V is the conditional cumulative distribution of the winning bid given the value. And if we integrate that object over values, then we're going to get back the distribution of the winning bid. And then this object is also a winning bid distribution conditional on the value, but it's times the probability that buyer I wins. So the interpretation here is HI of B given V is the probability conditional on the value that bidder I wins with a bid that's less than or equal to B. Right? And then, of course, by summing these across, some bidder is going to win. There's no reserve price in the auction. So if we sum these across I, we're just going to get back the probability that the winning bid is less than B. Okay. Now, the reason for doing this decomposition is that now we have a rich enough object to compute the surpluses of the seller and the bidders in equilibrium. So in particular, what is bidder I's ex ante surplus in the auction? Well, it's just going to be the integral over all winning bids times the probability that that bidder makes the winning bid of the value minus the bid, where we're integrating across all values and across all winning bids. All right? Does that make sense? Okay. So we want to use these upward incentive constraints in order to bound H, right? And we don't have enough information in just these marginal distributions over winning bids to talk about the merits of a particular pointwise deviation from bid B to bid B prime. But it turns out that we do have enough information to talk about the benefits of aggregates of those deviations. So in particular, we're going to look at the following kind of upward deviation. You're going to deviate by bidding, and we're going to call this a uniform upward deviation to a bid B, which means that whenever you would have bid something less than B in equilibrium, you bid B instead. If you were going to bid more, keep doing whatever you were going to do anyway, but you never bid less. Okay? Bid the maximum of your equilibrium bid in B. Okay, so this is a well-defined deviation in the normal form of the auction, and we can ask, what would your surplus be if you uniformly deviated up to B from an ex ante point of view? And it turns out that there's a simple expression for that surplus as well, and it's exactly what I've written here. So why is this the ex ante utility of the uniform upward deviation to B? Well, this expression we can think about this actually conditional on each value, and just look at this expression on the inside. So there are basically two possibilities. If you uniformly deviate up to B, you're always going to win whenever in equilibrium the winning bid would have been less than B, because you're bidding at least B, right? So whenever the winning bid would have been less than B, now you're going to win, and you're going to win at a bid of B. Okay. There's another possibility, which is that the winning bid would have been higher than B. And actually, on that event, you don't change the outcome or the surplus that you would have gotten. The reason is either this bidder who was bidding more than B and winning in equilibrium is still going to be bidding more than B, and they were outbidding you anyway, so they're still going to be outbidding you even if you increase your bid to the maximum of what you were doing before in B. Okay. So the bottom line is that we can obtain the player surplus by just essentially giving them all of those, a win on those events where the winning bid would have been less than B, even if some other player would have won, and but now they win at a bid of B. And I should say that whenever this particular bidder I was going to win, but at a bid higher than B, the deviation doesn't change their bid, right? So they're still going to win and get the surplus that they were going to obtain before. All right, so that means that bidders are not going to want to uniformly deviate up to B if this expression, which is the utility, ex ante utility from the uniform upward deviation, is less than or equal to what you would get in equilibrium. All right, and this is just a constraint on these winning bid distributions. Now, I don't want to keep tracking these bidder subscripts, and I don't really have to because all I want is a lower bound. So what I'm going to do is just sum this inequality across bidders to get one that only depends on h of b given v. And the reason I can do that is because now I'm just saying that this is a weaker restriction on the winning bid distributions, but it says that on average across the bidders, these n bidders wouldn't want to uniformly deviate up to b, which is a necessary condition for equilibrium. And then a little rearranging makes this a little simpler. The exact formula is not essential, but the point is that now I've ended up with an inequality just on these winning bid distributions, conditional on the value. All right. So this was all supposing, by the way, that there was no atom at B. Someone wins with a bid of B with 0 probability. If they were atoms, you can still show that this inequality has to hold by just taking approximations. So this is a necessary condition for all equilibria, even if that equilibrium was going to induce an atom. So let's let H star, script H star, denote the set of winning bid distributions that satisfy this constraint. Okay, they're obtained from conditional distributions of winning bids given the value that satisfies constraint. And what we're going to show is that, so obviously the set of all winning bid distributions is contained within this H star because we've just dropped a lot of incentive constraints except for this one that corresponds to an average uniform upward deviation. So the rest of the proof is just going to argue that H star actually has the smallest element in the first order stochastic dominance ordering, and it's H lower bar. And that'll complete the proof. Okay, so why is that? Well, here's a very important simplification. This was our constraint, and really what I want to emphasize here is that there's only one part of this constraint that depends on how the value and the winning bid are correlated. Okay, it had a bunch of objects that depended on the marginal distribution over winning bids, and we could integrate out the value, and it only leaves this one part, which is essentially, it's proportional to the expectation of the value conditional on the winning bid being less than B.
Can you say star again?
Yeah.
One more slide.
Yeah, I just need to adopt a light touch because the last time this clicker had a heart attack and we ended up in the appendix. So this is star. And this is roughly saying this is kind of what you gain, proportional to what you gain from the upward deviation, and this is what you're losing because you're going to have to, you're going to be bidding more and still winning on events where you would have won anyway. Right?
Okay.
Okay. Good. All right, so at any rate, this is a rearranged version of the same inequality, and the only way that correlation enters is on the left-hand side of the less than or equal to. and we care about what the expectation is of the value conditional on the winning bid being less than b. And you relax this constraint by making this expectation smaller. Okay. And it turns out that there's a particular way that you make that expectation as small as possible. You know, you want to associate the lowest values with the winning bids less than b, and you do that for every possible cutoff, b, by making the value and the winning bid perfectly correlated with one another. So in other words, we're going to make the winning bid a monotonic and increasing function of the value. That's going to minimize for every cutoff the expectation of the value, given that the bid is this value or lower. All right? And for any given h of b, you know, we could always come up with such increasing function so that we keep the same marginal distribution over the winning bid, but make this term smaller. Right? So what that tells us is that it's actually without loss of generality to restrict attention to elements of script h star that are induced by some deterministic and increasing winning bid as a function of the value. Notice we're kind of getting incrementally closer and closer to the solution we had at that candidate worst case, where it was in fact true that the winning bid was a deterministic function of the value because the value was the highest of the signals and the bids were monotonic. All right. So the last rewrite of this star equation is just expressing it in terms of the winning bid function instead of the distribution of winning bids. Again, not critical how we get there, but there is a way to write it so that it only depends on the winning bid function. And you can rearrange it to say that, that constraint is equivalent to saying that at every value, the winning bid at that value can't be too low, okay? And the lower bound is a function of the winning bid at lower values. That's the critical feature of this constraint. So we could actually define an operator that takes winning bid functions to winning bid functions and essentially says if you give me a beta, I'm going to give you back a new beta, which is the smallest one that satisfies this inequality. Okay, so you give me a winning bid function, and I'm going to define a new one which is just equal to the right-hand side of this equation. And then this inequality, is equivalent to saying that beta has to be at least lambda of beta, pointwise. Right? Now, two useful facts about this this lambda. It's monotonic. You know, if you increase the winning bid that you put in at every point, you're going to increase this integral and therefore increase the left-hand side. So what that means is that if you start with a winning bid function such that beta is bigger than lambda of beta, well, if you apply lambda to both sides of this inequality, it's still going to be true. Right? So that means that beta is also bigger than lambda of beta. So for any winning bid distribution that you could, is feasible, lambda is going to be decreasing at that beta. And in fact, if I were to apply lambda forever, I would just get a sequence of decreasing winning bid functions, all of which are also going to be feasible. Okay? And the other important fact is that this lambda is a contraction. Okay, it turned out that it's a contraction of modulus 1 over n. How can you see it here? Well, we're multiplying beta by a 1 over n here. Okay. So that means that if I start from a feasible beta and I just iterate this lambda operator, I'm going to get a decreasing sequence of functions, all of which are feasible, and they have to converge to the unique fixed point of this operator. So what that tells us is that the fixed point of this operator is, first of all, feasible, obviously, and it has to be below every other feasible winning bid function. And then it's easy enough to verify that beta lower bar is the fixed point. Okay? Yeah. I like this proof, if you can tell. Okay. All right. So that's the proof. That's it. You know. But you know, stepping back from a methodological point of view, I think what made this proof work is identifying the right constraints and then finding the way to pool them together in a way that gets us a lower bound that was hit by our particular construction.
So, can I think of, again, I mean, the details here are quite complex, I understand, but can I think of it in a sense, the fact that you go to correlated equilibrium is like taking the n betas together and having one player instead of all of them. In a sense, he is dictating the n tuple of actions. That's one way of looking at correlated equilibrium. And also, in some sense, he has the joint information of all of them, which, in some sense, in your extreme case, becomes knowing exactly the value, right? Because the aggregate information of all the players is the maximum, which is indeed the common value, right?
Well, actually, in our solution, in this particular correlated equilibrium notion, the mediator always knows the value. He could tell the bidders less than the value if he wanted.
No, I don't care. Okay, so
but
the mediator, yeah. So, right. But so in some sense, suppose that you had just one. So once I understand that, suppose you only had n equals 1. Let's try to solve that problem. Is it easy to understand what happens for n equals 1?
Yeah.
Okay, because I think
It's a first price auction without a reserve price.
Very good, very good.
Bid 0. I mean, you wouldn't be too smart if you bid anything other than 0 if there was no one bidding against you. Yeah.
Okay, then there is something else here at work, which I.
Well, I think the problem only becomes non-trivial if you have more than one
The
bidder.
correlation somehow replaces the n betas as 1. Yes, that's a
It kind of does, but at the same time, whoever's choosing this correlation has to respect individual incentive constraints. So you can only make recommendations so that every bidder by themselves, given their private information, wouldn't want to deviate.
Okay,
Let's come back.
guess we'll think about it.
Okay. So that's about. Oh, yeah, Elchanan?
I don't want to keep you, but can you say again what's the nature of this operator?
What is this operator? Well, this operator is basically saying. Okay, it's kind of saying, suppose that others' winning bids were held fixed in some sense. Like if they are selected to win the auction, then as a function of the value, they're going to bid something deterministic, and we're going to hold that fixed. And then we're going to ask for just bidder I, what's the lowest we could tell bidder I to bid in equilibrium such that it wouldn't want to deviate. So it's something like that. So that no one would want to deviate. It's something like that. Yeah. I think that's pretty correct. All right. So I have a lot of other stuff that I want to talk about. So I just want to wrap this discussion of robust predictions up quickly. Really this is meant to be a kind of illustration of what you can do with this technology. And then, the question is, what would you do with it once you have this answer? One thing you could do is try to compare different mechanisms. But maybe we don't want to compare them by revenue on a particular model of information. We want to compare them across, in terms of the set of possibilities across a number of models of information. And you could use this technology in order to do that, and we're going to talk about that more in just a minute. So for example, we have one paper that shows that actually in a similar framework, the set of outcomes of possible revenues that you could get is smaller with the FPA, with the first price auction, and higher actually than in many other standard auctions like second price or all pay. Another possible application is, so there's a large literature in I/O on saying, suppose we observe the distribution of bids generated by a particular game form, particular auction. What can we learn about fundamentals by trying to invert the equilibrium mapping? And in order to make that work, and in order to get a point prediction, you have to have in mind a specific model of information that's giving rise to the bids that you observe, like affiliated values, is a common assumption. So, one could apply similar, one could very well have similar concerns about misspecification of the model of beliefs in that context, in which case you might use this methodology to obtain a partially identified set of value distributions that's consistent with the bid distribution you observed.
Can I ask you something about that?
Yep.
If you look at maybe it's a trivial, absolutely trivial, but I would think that the most natural setup to start with would be one of not that where they have a common value, but that they say have the same distribution. Each one of them has a distribution.
Yeah.
Same distribution. On
Yes.
values.
Yes.
And then what do you get?
Good. So the answer depends on whether or not we're going to allow the bidders to potentially have no information, even about their own private value, as we have in this model, or are we going to insist that you at least know your own value? Okay. In the former case, the same techniques essentially work to get a lower bound. But rather than using the distribution of the common value as an input, you use a distribution of a statistic of the end bidder's values. Okay. And for all intents and purposes, the information and the lower bound look very similar. But it requires that the bidders don't learn their own value exactly under the true information. Now you could also ask what happens if you assume that the bidders know at least their own value, but maybe more, and that is a very hard problem. There are some simple cases where we were able to determine the solution, like for example if the value is only high or low. Okay. But more generally, the number of constraints kind of blows up because now, rather than having one of these uniform upward constraints for a bidder, now you would have one for each possible value that you have because you at least know your own value.
Yeah.
So in other words, you have to condition all of these incentive constraints on the value, and there, the solution is not so clean, actually. Yeah. But I think I bet there are things that one could say more precisely, but we weren't smart enough to figure out what those things are. But one of you probably is, so you should try it.
Could I just ask one more
Yeah.
question about that? Yeah, the third bullet point. So for the other standard mechanisms,
Uh-huh.
you get higher worst case revenues than lower.
You get lower worst case.
Revenues than for, but are the informational how do the informational what are the worst cases for those other?
Well, second price is easy because there are these collusive equilibria, and it's not so easy to refine them away because weak dominance doesn't really have much bite in a common value setting, an interdependent value setting. So any information is a worst case for that one. For all pay, I don't know actually. I don't know what the worst case looks like. I looked at it very briefly, but it didn't seem to be so.
How do you know that the worst case there is?
So it's an indirect argument that says that. So actually, if you look at the worst case information for the first price auction, there's an equilibrium on that type space.
For which
that
all pay is worse?
No, for which all pay generates exactly the same amount of revenue.
Oh, so there's another one that.
Yeah.
So it's a weak inequality.
It's a weak inequality, theoretically. There are simulations that suggest that it's strict, but we didn't go as far as to construct other information which is strictly lower. Right. In fact, yeah, I don't want to go into more. Yeah. Okay, so just to wrap up this discussion, there is other literature that's trying to do this robust predictions. There are a couple of papers that instead of looking at worst equilibrium given the information, look at the best, and then you can't use the base correlated equilibrium methodology in the same way. But all I wanted to say is that it's a developing literature. I think there's a lot of fruit, some of which is on relatively low branches, and it's a decent area to look at for dissertation topics. So that's it for robust predictions, and then I want to switch gears to the other topic for today, which we'll have to discuss in a somewhat expeditious manner, which is, so before we were saying let's fix a game form and try to make robust predictions for what happens if we don't know exactly the model of beliefs, okay, and we want a prediction for behavior that's going to be correct even if the true model is in some set of models. Part of the motivation was to kind of stress test the model and see how good or bad a particular outcome might be, depending on what we assume about information. It's a very different way of thinking about the performance of a game form or the outcome of a game form than the criteria that we usually adopt in mechanism design. Okay, so the usual model in incomplete information mechanism design is to write down a specific model of information and assume that that's, we're supposing that the designer thinks that's correct, and then the designer is optimizing the game form to induce an equilibrium that's most preferred given that information. Okay, but everything that all the motivation that we gave for concerns about model misspecification, you could equally well make those points in the mechanism design context. So the goal for this talk and for the literature that I'm describing is to capture that concern about misspecification in the mechanism design problem. And we're going to take a very heavy-handed approach. So it's not obvious what the right way is to do that. A very blunt way to do that is to say that this designer has a set of possible models that he or she thinks are possible, and the designer is going to evaluate a particular game form by the worst outcome across all of those models of information. This is a very pessimistic designer, and I think it's questionable whether or not we want to make such extreme assumptions. But as a kind of first step moving away from classical setup, this seems like a reasonable direction to go to see how our conclusions in the mechanism design problem would change. Okay, so this isn't like a new idea, actually. It's been around in the game theory and mechanism design literature for a while. One of the so I want to talk about two papers, basically, that try to do something like this. One is a paper by Chung and Ely, and it's also in the context of revenue maximization in auctions. And then I'm also going to discuss some recent papers by myself and co-authors, and in particular also Stephen and Dirk Bergerman, my co-authors on the first price auction paper that we were just discussing. So before we get there, let's review the standard model. So here's a discretized version of the problem of designing a revenue maximizing auction when values are discrete. Okay, so and here for now we are going to assume private values. So all of the bidders, they're n bidders for this single unit, and each bidder has a value vi, which comes from this discretized grid, and we're going to assume that the elements are equally spaced. They're delta apart, and then v0 is 0 as a normalization. But we're going to assume that everyone has values in this set. Could be that v1 is equal to 0 as well. Okay, and so mu is the seller's prior joint distribution over the buyer's values. Okay, and pi, m, is the marginal likelihood that buyer i's value is equal to VIM under this prior mu. Okay. VM, yeah, we don't need the I subscript here, and nor here. All right. Mu I m is the conditional distribution of the values of the bidders other than I, given that I has the mth value. And we can view this as just a vector where the coordinates of the vector correspond to different values of the others, different value profiles of bidders other than I. Okay. Now a mechanism, a direct mechanism, is going to say for every profile of values, what's the likelihood that each buyer gets the good, and what is the transfer that each buyer has to make to the seller. And we could break that up in the following manner. We're going to say value by value for bidder I, what is the likelihood that I gets the good as a function of the other's values. And we could similarly think of this as a vector with the same indices. And TIM is going to be the vector that denotes the transfer as a function of V minus I when I has the mth value. Okay. So that means that mu IM dot TIM is the expected transfer from I conditional on I having the mth value, right? Because this is the conditional distribution over the other's value profiles. This is the transfer that I makes as a function of the other's value profiles when we condition on I having the mth value. So expected revenue from the auction is just going to be the expectation across or the sum across all bidders, expectation across bidder i's value of this dot product. All right? So it's a slightly non-standard notation, but it's convenient for where we're going. So we want, right now, for now, we're going to be agnostic about exactly what the buyer's beliefs are. They've got some beliefs, and we're going to describe them just conditional on their values. So sigma im is going to be the beliefs of buyer I of type Vm about V minus I. And the reason why we want to specify beliefs in term is because we explicitly want to allow for non-common priors. Okay? If we had a common prior, then it would have to be that the sigma im, the beliefs of buyer m, would match that of the seller, but we don't want to impose that. Okay. So a mechanism is Bayesian incentive compatible if for every bidder I and for every type m and for every other type that you could report L, the expected surplus for bidder I is bigger than what they would get if they switched to L. Okay, in which case the allocation vector and the transfer vector would be the Lth one instead of the Mth one. And a mechanism is interim individually rational if all of these bidders expect to get non-negative surplus from participating in the auction, conditional on their value. Does that make sense? So we're just taking the dot product of the conditional distribution of others' reports times these vectors of allocations and transfers. Right.
What is sigma m? Sorry, what's sigma m?
That's the belief of the buyer. Buyer I type Vm about V minus I.
Vim, he does conditional on sigma m, not on mu im.
Exactly. We want to allow for the beliefs to be different.
Sigma m before, when you started saying what the expected things are, you have talked about beliefs.
No, I'm talking about beliefs from the perspective of two different agents. One is the seller. If the seller conditions on Vi, what is the
Vim is computed on the basis of the sigma, not on the mu. On sigma.
There is no.
I mean, TIM is an expectation. Your expected transfer given the expected transfer given that you're of type Vm. That I is of type Vm.
This is meant to be a vector, and it's a vector whose coordinates correspond to different values of bidders other than I. And it's saying for each of those other value profiles, what is the transfer that buyer I makes? And Qi says for each of those other value profiles, what is the probability that buyer I gets the good? Sigma I is a vector that says for every value profile of the others, what is the conditional probability of that value profile
So
given
these
Vm?
are v to the power n minus 1 vectors.
Exactly. Number of, or
Okay.
capital M to the
Okay,
power n
okay,
minus 1.
Okay, thanks. That's fine.
So
Okay.
the way you write it, what the I expects to make would be different than what the seller expects to get.
Precisely. That's right. Because if they were updating from a common prior with the seller, then the sigma im would be mu im, but it might not be. All right, it's an important piece of this model. Okay, so we're going to denote by RBIC maximum revenue across Bayesian incentive compatible and interim individually rational mechanisms. And this object implicitly depends on on the sigma i's, because that's going to determine the shape of these incentive and participation constraints and determine the set of feasible mechanisms for the seller. But RBIC is the best among them, best revenue.
So you're going over all possible profiles of subjective beliefs.
Correct. Or I'm not, but Chung and Ely will. Right, yeah. Okay, so in the common prior case, we actually know a lot about the shape of the optimal mechanism in such a setup. When values are independent, that case is essentially solved by Meyerson in a continuum formulation of this model. When there's a lot of linear independence, this should be for the sigma i's actually, but we're still in the common prior case in which sigma I is equal to mu I. So when those conditional beliefs are sufficiently linearly independent, then Kramer and McLean show that the seller could actually extract all of the surplus from the buyers. And then in between those two cases, there are some nice extensions that were done by Vitor Farina Luz, kind of combining those two constructions. What's that? Okay, and possibly others. This is not meant to be an exhaustive list. Outside these cases, and possibly some others that Vasiliki knows better than I, we don't know. So it wouldn't be correct to say that we know for all mu's what is maximum revenue and what is the optimal mechanism, beyond knowing that it's the solution of a linear programming problem. When we go outside the common prior world, or even when we go outside the sort of simple cases from Meyerson's analysis, the optimal auction can be very complicated, and the seller can, the particular form of the mechanism, in order to leverage this independence, it depends in a very sensitive way on the beliefs of the buyers. And even when you're in the IPV model, but you have asymmetric distributions or irregular distributions, exactly how you want to favor one bidder or another becomes complicated as well. So the point is that this model puts a large burden on the seller and the buyers to have the correct model of beliefs, to know exactly how to calibrate this mechanism. So it makes sense to look for other mechanisms that are not going to be as sensitive to assumptions about information. So one extreme that you could go to would be to say that you want to find a mechanism that's going to satisfy these constraints regardless of what the beliefs are of the agents. That would be a very extreme reaction. So such a mechanism, whether or not the bidders would want to play it as the seller thinks they will play it, doesn't depend. Whether or not they'd want to tell the truth doesn't depend on what their beliefs are. Okay. So this would have the benefit of relaxing demands on the seller's knowledge to figure out how to design such a mechanism, but also making the strategic decisions simpler for the buyers. And one class of such mechanisms would be those that have truth-telling as a dominant strategy, as a weakly dominant strategy. So a mechanism is dominant strategy incentive compatible if these constraints that had to hold before only an expectation, if we dotted with the sigma IM, the buyer I's beliefs, if these inequalities have to hold component-wise, meaning for every profile of the other's values, you're better off reporting truthfully than misreporting. And similarly, we can get an ex post version of the participation constraint by requiring that the surplus has to be non-negative component-wise for every value of the others. And obviously that means that if you take the expectation of those vectors, it'll also satisfy these constraints. All right. Yeah.
So, in the standard model, when we have a common prior,
Mm-hmm.
we know that in this environment, for any Bayesian feasible mechanism, we can construct an equivalent dominant strategy incentive compatible.
I think you need more than just common priors. I think you probably also need independence.
We need,
You definitely need independence.
okay, that's true. So that's basically why here it becomes relevant.
Absolutely, because we want to allow for the possibility that if the seller really knew beliefs, he could do a lot more in the style of Kramer and McLean.
Thank you.
Okay, so these constraints imply the interim versions that we had a few slides ago, obviously. So if we let R DSIC denote maximum expected revenue across all dominant strategy and ex post IR mechanisms, then it has to be that for a particular model of beliefs, the seller could do better with a Bayesian mechanism than he could with a dominant strategy mechanism. Okay. So just a couple of observations about what is the optimal dominant strategy mechanism. It has a couple of well-known features. First of all, there are always going to be binding incentive constraints, ex post incentive constraints, to deviate down, to deviate to the next lower report. Okay, that's a general feature. And also, the lowest type that has the lowest value is always going to be indifferent ex post between participating and not. So what that means is that actually you can pin down what the transfer is as a function of the allocations. And that transfer is basically the surplus that buyer I generates from being allocated the good and consuming the good, minus some discount, which is an information rent that the bidder gets, that the seller gives him in order to induce him to not misreport. This is exactly the form of the information rent. It's an integral of lower allocation probabilities. Now, for time constraints, I'm not going to go through it. I'm going to go through it very quickly. So that's it. But it's a standard result, so you can look it up in the textbook. But what's important to note here is that as the seller increases the likelihood of allocating to a type M, the transfer is going to increase at a rate of VM for that buyer, but the transfer is going to go down for the types with higher values at a rate of delta for every one of them, actually. So if the seller wants to allocate to a particular type more, he can get a little more surplus through the transfer from that buyer, but he has to give others greater subsidies. So the net contribution to revenue from the seller's point of view from this allocation probability is actually a sum of what the seller is going to get on average from buyer M minus the subsidy that has to be given to higher types. Okay, and this is commonly called a virtual value. But the way we're defining it here, it's a kind of interim virtual value from the seller's perspective, but having derived this formula from the ex post constraints. So expected revenue for the seller is just the expectation of this virtual value summed across buyers and dotted with the allocation probabilities, full stop. All right, so those were necessary conditions, that you have a downward binding constraint and IR binds at the bottom. So, the allocation, the transfer was always going to have a form such that this formula is true, but that doesn't mean that the seller could pick any Q that he wants, because there are other constraints that will also have to be satisfied, and we don't know whether or not those are binding. And a well-known necessary and sufficient condition for a given allocation to be globally incentive compatible, to satisfy all of those dominant strategy constraints, is that it's increasing in M, component-wise, which is going to be true. And if this virtual value is increasing in M, then even if the seller ignored all of those other constraints and just tried to optimize this formula here, the seller would end up with an increasing Q. Okay, so we're going to look, so that's called the regular case, when these virtual values are increasing, and in that case, the point-wise solution to that optimization problem is actually the global solution. All right, so that's all I will say about that. This thing is having heart attacks again. Okay, good. So, so this dominant strategy does capture the idea of robustness to misspecification of beliefs. It may be stronger than we would like, because we really started off with this max-min motivation, and maybe there are other mechanisms that do better in a max-min sense than these extreme dominant strategy ex post IR mechanisms. But this paper by Chung and Ely shows that actually there is no gap. So there is a way of, there is a max-min designer who would optimally choose a dominant strategy and ex post IR mechanism. Okay, and they're exactly studying the case where, so they're studying the case where actually there are no restrictions on the beliefs of the buyers. It could be anything that doesn't conform, and need not conform to the seller's prior. And the seller is going to evaluate a given mechanism in tight space according to his most preferred equilibrium, but looking at the worst case of that most preferred equilibrium across belief structures for the buyers. Okay.
Sorry, does this allow the buyers to believe that the other buyers all have very low valuation?
Yeah, that's one possibility.
So how could there be a max-min mechanism that yields a positive?
Well, the dominant strategy mechanism is going to be incentive compatible and will yield a positive revenue for the seller. But maybe you could do better. Okay. But yeah.
If you have to be, the mechanism has to be incentive compatible for all possible beliefs.
Yes.
It has to be incentive compatible for extreme beliefs, and doesn't that give you this weak dominance? In other words, I would believe with probability 1 that the proper parts of the others is so broad, and then I should be off. So doesn't that, from the point of view of the designer, I could have each one of those probability 1 beliefs, and hence isn't it clear that each should be, that this is
Okay,
the
if I wanted, so here's the wedge. I understand.
It's not surprising.
I understand what you're asking, and here's the wedge. Your question is, what do I need a mechanism to do in order for truth-telling to be an equilibrium for all belief profiles? And in that case, it is obvious that it has to be dominant strategy. Okay, but that's different from saying, here's a mechanism. Maybe the equilibrium is going to be different. You know, maybe these guys don't want to tell the truth for all belief structures, but still I can compute some expected revenue of whatever the equilibrium is, the non-truth-telling equilibrium. Yeah. In other words, we're not insisting that the mechanism be a direct mechanism for every model of beliefs. Does that make sense? Okay.
What do you regularize here? I don't see.
Exactly. So we'll see why regularity is a necessary hypothesis. Well, it's not necessary, but if you relax it, then you can find counterexamples. I'm not going to give the counterexamples. They're in Chung and Ely's paper. Okay. All right. So the theorem of Chung and Ely says that if you start with a mu that is regular, then there are beliefs of the buyers so that the seller can't do any better than running a dominant strategy, an ex post IR mechanism. So what that tells you is that if since this is always a possibility, this particular model of beliefs, then in general, no matter what mechanism the seller picks, he can't do better than the expected revenue he would get with a dominant strategy mechanism. Okay? So we're not going to prove it completely, but I'm going to try to give you the intuition for their argument. So such a seller would optimally, a max-min seller would optimally choose an ex post the dominant strategy mechanism. Okay, and in fact, we're going to show this for an even easier problem for the seller. We're not even going to assume that the seller has to choose Bayesian incentive-compatible mechanisms. We're only going to require that the seller choose mechanisms so that the bidders don't want to deviate to the next lower report. In other words, we're only going to look at those local downward. We're only going to require that the seller's mechanism satisfy local downward constraints. This is an easier problem for the seller, and even with that easier problem, the seller can't do better than the dominant strategy mechanism. Okay, so this PI, capital PIM, is the probability that buyer I's value is greater than or equal to VM. And here is the worst case model of beliefs. A type M is going to have a belief which is the average of the seller's beliefs for higher types. Okay, so remember that this is the belief that the seller would have in this buyer's shoes, and the buyer's actual belief is going to be the average of those beliefs for his own value and higher values from the seller's point of view. This seems very arbitrary, but it turns out that this is the right one to do. Okay, so for future reference, there is a recursive formulation of this, because as we increase m, we're just changing the indices in the sum. Maybe the formula of this recursive relationship isn't too important, but it's there. I guess my temptation is to put more algebra in the slides than would be optimal for a talk, because I know that this talk is going online, so one can go back and try to understand the algebra a little bit better ex post. Okay, and also, the seller's beliefs, marginal beliefs over the values of others, of the values of the bidders other than I, is exactly the belief of the lowest type. Okay, because that lowest type is doing this averaging over all of the values. So it's going to turn out that this is the worst case, a worst case model of beliefs. And if these are the buyer's beliefs, then maximum revenue in a Bayesian incentive compatible mechanism is going to be equal to maximum revenue among dominant strategy mechanisms. Okay, so I'm going to sketch their proof for the generic kind of Kramer-McLean case where these beliefs of the seller are linearly independent. Right? It's important. And actually, if the seller's beliefs would be linearly independent, it implies that the buyer's beliefs would also be linearly independent, because these buyer's beliefs are essentially taken by averaging increasing subsets of the buyer's beliefs. just over M. So this is looking at each bidder.
Fix I, and then look at this belief for different values.
Correct.
They're independent.
They are linearly independent. Exactly.
Rank condition.
It's a full rank condition. Exactly. And this isn't necessary, but it simplifies the proof considerably. Okay. But the point is that if the seller's beliefs are linearly independent, then the buyer's beliefs will all be linearly independent as well. What's that?
Small n is bigger.
Here, it is a typo. Thank you. Otherwise, that would be true more generally. It would be true more generally. Could use weaker assumptions. Okay. All right. So there are basically 3 steps for their proof, which I think I can do. Okay. So suppose we have a Bayesian and incentive-compatible mechanism for this model of beliefs. Okay. Whatever mechanism the seller is going to use is going to induce some direct mechanism for this model of beliefs, and that's what we're looking at, the associated direct mechanism. My claim is that, it's without loss of generality if the seller knew that these were the beliefs to assume that these interim IR constraints bind for every I and for every M. In other words, all of the bidders are indifferent between participating and walking away. Now, why is that? Well, okay, so under this mechanism, this is the surplus that a given bidder I with type M gets from participating in the auction, right? And my claim is that, from this linear independence, there's going to be a single lottery, lambda I, that we could find, such that we're going to solve a system of linear equalities that correspond to this for every M, right? This is just coming from linear independence. Okay, so I can find this one lottery that's going to have expectation equal to the interim surplus for every of each buyer from their perspective, from each type from their perspective. So what I could do is take this lottery and just tack it on to the transfer that the seller was using before to create a new transfer. And obviously, this new transfer is going to extract all of the remaining surplus, or it's going to net out the surplus of the buyers, and they're all going to be getting 0 surplus in expectation. And this hasn't changed incentives because all of the transfers get the same additional lottery. So whatever you report, as long as you're participating in the mechanism, you're also going to get this additional piece. And also, actually, from the seller's perspective, this has to be increasing revenue because the expectation of this lottery from the seller's perspective is the same as the expectation of this lottery from the lowest type of buyer's perspective, which has to be non-negative, because the participation constraint is satisfied. So the seller could always reduce lotteries or make the participation constraints bind and be better off. You notice that the fact that the seller is better off only depends on the fact that the lowest participation constraint is satisfied. So in fact, the seller could have changed this lottery in order to make the participation constraint for the lowest type bind and give whatever surplus to the higher types, and still it would have been an improvement. So there's a degree of freedom from the seller's perspective. The seller doesn't really care what the surplus is of the higher types conditional on the lowest type. Okay. Also, so that's step 1. There are 3 steps. Step 2 is from linear independence, you could always make these downward constraints bind, and that would be beneficial. And the argument there is, again, coming from linear independence, we can always find a lottery that has a negative or a positive payout. This should be a positive payout if you have the beliefs of type M, and has a 0 payout if you're any other type. Okay. So now if we want to make a type M indifferent, if we want to make a type M indifferent to, let me just back up. If we want to make a type M indifferent to reporting M minus 1, what we can do is just increase the transfer if you report M minus 1 by this lottery and make it worse, make that report worse from the perspective of bidder M, but the same from the perspective of any other bidder. And we could always do that exactly so to make the expected payoff from reporting m minus 1 equal to the expected payoff from reporting m from type m's perspective. Okay, and it's also the case that this increases the seller's payoff, which I won't go into in detail.
The lambdas have to be non-negative or they are?
No, it can be anything. But I have linear independence. Okay, good. So now we're basically at a point where we know that it's without loss of generality to assume every type has a binding participation constraint, every type is indifferent to reporting one lower type, and that allows us to actually solve out the transfers. You know, we have that these 6 equalities, I suppose, but only 2 of them really matter, hold, that you get, each type is going to get 0 surplus whether they report their true type or report the next lower type. And what that means is that we can solve out for each type their transfers in terms of allocations, similar to we were doing in the dominant strategy case. And if you solve out those expected transfers in terms of expected allocations, you can show that from the seller's perspective, the expected transfer of a type M is equal to the virtual value that you would have had under the dominant strategy mechanism, which is a little bit astonishing. This is a different transfer than if the seller used the dominant strategy mechanism, okay? But it's the same net contribution to the seller's revenue as if the seller had used the dominant strategy mechanism. And this thing is having a stroke. Okay. And there was the derivation. I hope you got it all. Okay. But, you know, it sort of comes mechanically from a relatively simple sequence of adjustments here. That's the end of the proof. Expected revenue has exactly the same form in terms of the allocations as it did in the dominant strategy case, which proves that the seller can't do any better than the dominant strategy mechanism. Okay. So, so I just want to talk for a couple of minutes about, you know, why this works, because it's kind of a mysterious result. And I've talked to other people, and a lot of people seem to share my feeling that it's a bit of a mysterious result. So one important thing is that even though the seller can extract all of the surplus until these constraints bind from the buyer's perspective, that doesn't mean that the seller is getting all the surplus. Okay? In fact, the seller is going to have to leave some surplus on the table from his perspective in order to make those constraints bind for the buyers. And in particular, you know, you can show that under those assumptions of binding participation and binding local downward constraints, actually you can solve out the transfer in terms of the allocation. And if we don't substitute in the buyer's beliefs, then it has this form, which is expected surplus from allocating to this buyer minus a discount, minus some incentive discount. Okay, and of course we concluded that this was equal to the virtual surplus for the beliefs that we chose. And in fact, those beliefs are chosen precisely so that this discount that the buyer gets exactly corresponds to the discount under the dominant strategy mechanism. So that makes it a little less mysterious where those beliefs are coming from. You know, also, logically, it has to be the case that there's multiplicity of optimal mechanisms on this type space. Why? Well, we know that there's a Bayesian mechanism that's optimal that makes all of the participation constraints bind. The dominant strategy mechanism also has to be optimal, and the participation constraints would not bind, right? That would actually give rents to higher types. So how are those both possible? Well, there was this critical step when we made the participation constraints bind. It didn't actually matter what the seller was doing with the interim expected surplus of types above the lowest type. Okay, so that was a free variable, and presumably we could have chosen those interim surpluses differently so that we would have gotten back out the transfers that the seller uses in the dominant strategy mechanism. Okay, but making the participation constraint bind is a useful normalization sort of to make the algebra go easier, which I'm sure you all felt. All right, so I have about 15, or let's say 20. We'll round up to 20 minutes left. So I want to talk about a complementary model of Max-Min auction design. So this is a really beautiful result, and it's insightful, but it does require some strong assumptions. You know, it requires regularity, first of all, and you know, the regularity was coming from the fact that this reduced objective, oh, whatever, this reduced objective coincided with the objective under dominant strategies. That would not be the objective under dominant strategies exactly if you had an irregular distribution. But it also relies on private values. It relies on non-common prior, and maybe we don't want to assume that their beliefs could differ that much. And it also assumes that, the seller thinks that these bidders are going to behave in a way that favors him, conditional on their beliefs. So they show that, Chung and Ely show that certainly the regularity and the non-common prior are essential, and if you relax those, you break the result. There's a recent paper by Chen and Lee who give a dual interpretation of when this result is going to go through, this Max-Min foundation for dominant strategies with other applications. But I would say,
By dual interpretation?
well, the mechanism design problem is a linear programming problem. It has a dual, and it turns out there are nice ways of interpreting these necessary conditions, or these sufficient conditions in that dual problem. Okay. But really what I want to talk about is what happens if you had made alternative assumptions about the environment. What if, like in our first price auction discussion, we had common values, and what if we imposed a common prior, which is implicit in the Bayes correlated equilibrium solution concept we were using? And what if instead of assuming that the equilibrium selection is the best for the seller, what if it's the worst? Okay, we can ask, what would happen? What would happen to Max-Min mechanisms with those alternative assumptions? Now, weak dominance, dominant strategy incentive compatibility has basically no bite whatsoever in a common value environment because, you could assign very small probability to having a type where this action is good, which would make it not dominated. And in general, weak dominance is not going to rule out lots of strategies. So, there's going to be we might expect that there's going to be a qualitatively very different kind of Max-Min mechanism that we get with these assumptions. Okay, so here's the model. It's 2 buyers, very simple model. This is the simplest model, I think, in which one could try to explore this problem. Pure common value, which is either 0 or 1. The 0 is an important normalization, actually. It's not a normalization because it means that in the low value case, it doesn't matter who gets the good, the buyer or the sellers, from a surplus point of view. And there's a probability P that the value is 1. And the seller evaluates each possible mechanism by the lowest revenue across all Bayes correlated equilibria, basically. And then R star is the Max-Min revenue from the seller's perspective. All right, that's the basic setup. So this discussion, I should say, is based on a recent paper with Stephen and Dirk that's called Informationally Robust Optimal Auction Design. And there's follow-up work I'll talk about in the last couple of minutes. So as in the Chung and Ely model, we're going to try to solve this problem. This is really like a zero-sum game between seller, who gets to choose a mechanism, and nature, who's choosing the information and the equilibrium, and they have opposed interests. And we're going to try to solve that zero-sum game. We are going to solve that zero-sum game by constructing a saddle point, meaning a pair of a mechanism for the seller and information that nature could choose, so that there's no other mechanism that the seller could use that would do better given this information, and there's no other information that nature could pick that would induce a lower expected revenue given this mechanism. Okay. Guarantees the seller R star. Something is missing. If it just guaranteed him this, then it wouldn't be a very good mechanism, actually. All right. So let's start with the information. What is going to be unfavorable information for a seller who has this kind of problem? Okay. So this information, this type space, has to hold the seller down to a relatively low level of revenue, regardless of the mechanism. And an intuition which really just comes from zero-sum games is that we might think that there are going to be lots of optimal mechanisms at the saddle point. Some indifference on the part of the seller. The reason being just, if it doesn't have to be the case in zero-sum games, but it's frequently the case that, if there's some action that stands out as being superior to the others, then maybe the opponent could modify their strategy in a way that reduces the advantage that the best action has. And it turns out that that is true in this model, that there is going to be lots of indifference at the saddle point. Also, we want to allow for, in principle, very general type spaces, including type spaces where maximum revenue is difficult to characterize, but we're going to get lucky that the worst case type space is a nice type space. So what do I mean by nice? Well, we're going to look at type spaces where these bidders get one-dimensional real valued signals so each bidder I gets a signal that's drawn from some Fi and independent. Not necessarily symmetric, but it doesn't matter. And there's going to be a nice function that says what is the interim expectation of the value conditional on the two bidder signals. Okay, and we're going to denote it by W of S1, S2. This is basically the posterior probability that the value is 1, conditional on this pair of signals. Because remember, the value is either 0 or 1, so the interim expectation of the value is just the probability that it's 1. And of course, there's a necessary condition that will have to be satisfied by this W function, which is that P, the prior probability that the value is 1, has to be equal to the expectation of W. All right? We usually call that the law of iterated expectations. Okay. So what is revenue on such a tight space? Well, in the private value world, we're not in a private value world, but in the private value world, we know that revenue is the expectation of a virtual value of the buyer who gets allocated the good, right? Where that virtual value has this form. It's that buyer's private value minus this inverse hazard rate, okay, which is similar to the computations we were doing before in the discrete model. In this interdependent values model, it turns out you can generalize that virtual value formula, and it becomes this one down here. Let me try to interpret this bad boy. So now we're conditioning not just on the buyer's own value, but on the pair of signals. But otherwise, this formula has a lot in common. There is a value, which now is the common value. It corresponds to this one up here. There is an inverse hazard rate, which corresponds to this one up here. But there's this extra term, which is how sensitive the value is to your own signal. No, I'm not going to go through that in detail, but it comes basically from going through the same steps that give you this one, except here there's a normalization that your signal is your value. So when you take this derivative, it's just 1. Okay, but in general, this term doesn't drop out. So why is that useful? Oh. Well, it's useful because this virtual value is going to allow us to identify type spaces in which there's a lot of indifference for the seller about how to allocate the good. So we could always adopt a normalization that the distribution of the signals is exponential, and just make this W a function of the inverse of whatever transformation gets us to an exponential distribution. Why exponential? Well, exponential makes it so that hazard rate is constant and equal to 1. So it drops out from the virtual value, which will just be W of S minus partial W of S partial SI. Okay. And then I'm going to look at a very particular functional form for W, which is the following. Of course, this W can't be larger than 1, right? Because 1 is the highest. This is the probability that the value is 1. If we had a tight space that gave us probabilities higher than 1, then, we would be concerned. So we don't want it to be larger than 1. But as long as it's less than 1, it has this form, a constant times an exponential of the sum of the signals. Now that seems a little bit arbitrary. Why are we doing that? And A is being chosen to satisfy this law of iterated expectations here. Why are we doing that? Well, it turns out that this virtual value is going to be 0 for both bidders whenever the value is less than 1, whenever the W is less than 1, and it's 1 when W is equal to 1. Why is that? Well, remember, under this normalization, we have that the virtual value is just W minus partial W partial S, I. Now, when the W is constant and equal to 1, you know, this is 0 and this is 1. So that vindicates what I told you. But if we're below, this is basically going to be, you know, if you have any function that's a function of the sum of the signals, then this expression is just going to reduce to f minus f prime, which means that our function has to have an exponential form, right? So this W is reverse engineered in order to make the virtual value 0 whenever the value is less, the interim value is less than 1. Now, why is that interesting? Well, we want a type space. We think we might want a type space where there's lots of indifference on the part of the seller. If the virtual value is 0, it means that the choice of the allocation on this event doesn't affect revenue at all, either way. The seller is happy to give the good to buyer 1, happy to give it to buyer 2, or keep the good. All of those have exactly the same contribution to surplus. Okay? And when the value is 1, it's still the case that the seller is indifferent between allocating to buyer 1 and buyer 2. So basically it means that there are lots and lots, there are going to be lots and lots of optimal mechanisms. The only requirement to be an optimal mechanism on this type space is that it has to be that the good is allocated to someone when the value is 1, but it doesn't matter who. Okay? So this is a hard type space. Yeah?
So basic question. I understand. Why do you always normalize distributions?
Well, think of it. Here, so here's an even simpler example.
Always.
Always. I mean, I could have made the signals uniform as well, for example, in which case we're basically saying that we're going to make this W a function of the percentile of the signal rather than, you know, but any other normalization would do. Strictly monotone.
Doesn't matter. Just a parameterization of the informational content. That's all you use it for.
What he said. Yeah.
Thank you.
Exactly. All right. Good. All right. Now, it turns out that this is actually the worst case. We haven't proven that this is the worst case. The proof that this is, but you know, under the hypothesis that this is the worst case for the seller, we can compute max-min revenue, which is, you know, we said the only requirement for an optimal mechanism is that the good is allocated with probability 1 when this interim value W is 1. So maximum revenue is just the expected probability that W is 1. Okay, that's what R star is under this particular, yeah?
Can you get any mileage out of excluding weakly dominated mechanisms as a secondary criterion?
No, so I said this briefly before. When you have interdependence in preferences, weak dominance doesn't rule out very much. And the reason is that, you know, it has to be that, you know, this strategy is going to give me a lower payoff regardless of what others are doing, regardless of the strategies that others are doing. Others might have a lot of information about my value. And so I might want to choose a particular action because, you know, most of the time it's not inducing a very good outcome. Maybe there's something else I could do that would do better for lots of strategies of the others. But there is one strategy where this is a good thing to do, even if that seems like an outlandish strategy. And that would be enough to, you know, not be able to rule out the strategy as weakly dominated.
I was thinking from the principal's perspective, though. There's a large family of max and optimal mechanisms for the principal.
Mm-hmm.
Sometimes in these problems, it's the case that even if you have multiple optimal ones according to the max min payoff, that some of them are weakly dominated by others in that set of optimal mechanisms.
Oh, I understand what you're saying. I understand what you're saying. You're saying from the seller's point of view, are there mechanisms that do better, that do at least as well in this max-min sense, but for particular models of beliefs, they do even better?
Yeah.
And the answer is definitely, definitely. There's going to be a large set of max, because you could always tack on bells and whistles that don't do anything at the worst case, but do better in some event. Tillman Borgers has made this point very eloquently. You know, I could always take my mechanism and then add on extra reports which have the form, do you want to take a bet or don't you? And basically the bet is of the form, Eric wants to make a bet against Sergio, and Sergio wants to make a bet against Eric, and I get a cut if they both agree to make the bet. Okay, so I can't lose money on this bet, and they would both want to make the bet if they have non-common prior beliefs about the payout of the bet. You know, I could always tack on things like that that could never possibly lower my surplus, and these guys would be willing to do it for some crazy beliefs. So I think what that tells you is that it's not really a well-posed question to ask what is the undominated mechanism in that class. I think there are reasons outside the model why we wouldn't want, for complexity reasons, to add too many bells and whistles of that
It
form.
doesn't sound like it's super.
Right, right. Okay, a couple minutes left.
Can I just ask
Yeah.
that? So, it's very lovely set of tricks. Is there any chance of generalizing beyond the case of two possible
Yes.
values?
Yes, so so far, there's a generalization to n bidders and many values under the assumption that the seller has to sell the good. Okay.
But the seller doesn't want to.
What if the seller doesn't want to? I don't know yet, actually. I mean, there's certain, of course, if this were the distribution of the value, the one that's induced by this, then obviously this is still going to be a worst case. But beyond that, that's an open question that I'm working on at least. But I think there is the potential to solve it. But it's not known yet. Let me just press on for a couple more minutes because I'm almost out of time, and I do want to tell you something about the mechanism. Okay, so the formal proof that this is the worst case is the construction of a mechanism that guarantees the seller at least this amount of revenue, no matter what the information is, and no matter what the base correlated equilibrium is. Derivation is too involved to and even if I have a luxurious 2 minutes left. But I'm going to tell you what the mechanism is and tell you sort of the style of the argument. So here's the mechanism. The buyers are going to make reports, and we can think of those as being demands. I'm asking for this amount of the good, a probability of being allocated the good, and that's this MI. And there are two cases for the allocation. If the demands sum to less than 1, then there's enough supply of the good to fill both the demands, and each buyer gets their own demand. If it sums to more than 1, then the seller doesn't have enough supply to fill both, and instead what he's going to do is try to fill the demands as much as possible in a random order. So with the probability 1/2, buyer 1 is going to get his demand, he's always going to get his demand filled, and then buyer 2 gets whatever's left over, and then with the other likelihood, right, full stop, that's it. Here's a gratuitous picture of what this allocation looks like as a function of the reports made by the buyers. It's increasing in your report linearly as long as the sum is less than 1, and then it's increasing at half slope when they're incompatible. This is buyer 1's report. This is buyer I's report, and this is J's report, and this is QI. So as I's report increases,
What's the geometric shape I'm trying to understand from that? Bends upwards or downwards on the diagonal?
it bends downwards in MJ. It's always increasing in MI.
Like that.
Yeah,
Okay.
exactly.
You can't see it from
Exactly. The transfer rule is a little more exotic. Okay, it has this exponential form. It can be parameterized this way. It has a closed form expression essentially as an integral of this function phi, where you guessed it, this is phi. And I now realize that I didn't tell you what gamma is, but it doesn't really matter that I didn't tell you what gamma is. I'll put gamma up on the slides that I post online for your own, or you can just look at the paper. So this is a little peculiar. Why? And this is what this transfer looks like, actually, in case that helps it make more sense. So why did we choose this allocation and transfer? Well, basically, this allocation and transfer does two things. The first is the problem of minimizing revenue across base correlated equilibria is a linear program, right, where nature is trying to minimize revenue across all BCE. So if you want to get a lower bound on that problem, an easy way to do that is to look at the dual of this linear program. And it's well known, duality in linear programming, that the optimal value of this dual is weakly less than the optimal value of the primal problem, right? So if you construct any solution to this dual problem that's a feasible point for the dual, then it's going to give you a lower bound on optimal, on minimum revenue in the primal problem. So this allocation and transfer is basically reverse engineered so that there's a simple feasible solution for this dual problem that corresponds to an objective of R star, which is a proof that the minimum value for the primal has to be at least R star. Okay, that's not enough. I could come up with mechanisms, it turns out, that are feasible for this dual and don't have equilibria, which is a little bit shady. What that would mean is that actually this primal problem is infeasible for nature, and the optimal value for the dual is infinite. I consider that cheating if I solve this problem by making it so that there is no solution. Although clever, it does get some points for cleverness, but it's not quite satisfying. So in other words, so the other feature that this mechanism satisfies is it ensures that there is a Bayes correlated equilibrium. And it's basically truth-telling. It basically makes it so that this mechanism is a direct mechanism on that min-max type space. So that's the style of the argument for how to derive and prove that this is a max-min mechanism. And the last thing that I'll say is, what is the striking feature that comes out of this? Well, it's a very different mechanism, obviously, than one gets out of the Chung and Ely solution. The most striking feature that I think it has is that the allocation probabilities tend to be interior. It's almost never the case that you're going to get the good with probability 1 or probability 0 for different messages. And if the sum of the messages is less than 1, there's going to be positive probability the seller keeps the good. Now, why would you think that's a good idea? And I think that is part of the robustness of this mechanism. And it's very different from, say, first and second price auctions, where the allocation is either going to go to this bidder with probability 1 if they have the higher bid, or this bidder with probability 1 if they have the higher bid, or 0 if the bids are below the reserve price. The problem is that bang-bang allocation makes those mechanisms vulnerable in environments where bidders are often going to separate. I don't know about often, but in lots of examples, the bidders are going to separate, and the bidders who are more optimistic about the value bid more aggressively. But your optimism about the value is different from the rents that you get in equilibrium, right? Those rents also depend on sort of how sensitive the value is to your information. As in the case of first price auctions, it would, or second price, that's going to determine how much bidders shade relative to their expectation of the value. And in the bad environments for revenue that we constructed for the first price auction, it was the most optimistic bidder who had the most precise information about the value. The most optimistic bidder had the highest signal, which was equal to the value, and that led to very aggressive shading. Okay, so what this mechanism does is it smooths out the allocation so that it's harder to find environments where the allocation is going to be distorted towards those bidders who have the highest information rents. All right. There's ongoing research on this. There are a few papers that are studying, there are a bunch of papers that study this model in the single buyer case. Studies the many bidder limit of this problem. There's an earlier paper, actually, that studies the many bidder limit of this problem and gets some beautiful results there. And then Songza and I are also working on extensions of this model. And and I think there are a lot of interesting directions to go. So I'm just going to flash a bunch of questions that I don't know the answers to, and I don't know anyone who knows the answers to them. So, this is not going to be, I think, the end point of mechanism design, but it's an interesting direction to go and somewhat of a different direction to go than the classic literature. So that's it. Thank you.